All right, so welcome to EE220D. I'm going to cover some fundamental stuff, but before we do that, let's show you how to find the videos. So if you see this website here, cmosedu.com, and you click on videos, and here you go down and you see LTSPICE tips and videos. Then here, 220D. Okay, so if we go, I've already recorded the one. If you need the other, you probably all got it via email. Okay, so what I'm going to do today is I'm going to do the second version, but let me go ahead and save the sim examples here so that we have them from the first example, or from the first lecture. Now, just honestly, how many of you have watched the first video? Okay. So I'm going to go through a little bit of a review, but what I want you to do is I want you to understand what's going on, because in the semester, as you go through, if you're working your problems and you want to know if you got the right answer, it's very easy to simulate and see if you're getting something that matches your hand calculation. So before I do that, let's do a quick review. Let's just talk about, and you haven't talked about Ohm's law yet, right? Okay. So I'm going to try to give you a little bit more advanced discussion of what we did last time. But so this, let's call this, and let's be consistent. So hopefully this will be useful, but what did I write the last time? EE220D video 2, okay. So this is EE220D video 2, and what we're going to talk today is Ohm's law again, and then voltage dividers, and using LTSPICE. Okay, so let's just do a quick little review. Let's put a simple circuit down. Let's take a 9-volt battery. Just out of curiosity, what's the shape of a 9-volt battery? Yeah, it's a rectangle. Everybody knows that. When I was a kid, we used to call those transistor batteries because they were used for the transistor circuits. And then we're going to connect a wire up, and then we're going to go to a resistor. What's a simple example of a resistor that you'd use every day in your house, maybe? Toaster, heating element, heater, all that, right? The water, or the current that flows in the circuit, flows in this direction. In reality, that's a lie. And it's a lie because the electrons leave the minus terminal and they flow back around through the resistor, and we draw our electrical current flow opposite to the flow of electrons. So everybody follow? You probably saw that from physics, right? Okay, so if I ask then what's the current that flows from last time, it's the current equals the voltage over the resistance. Okay, so easy review. Let's go sketch this, and then I want to talk about measuring the current and how you can do that in LTSPICE. And I want to look at the net list so that you get used to troubleshooting and being able to look at net lists as you're doing things. So let's start it from scratch. So I have my LTSPICE right here. What do I hit first? File, new schematic. Then first thing I'm going to do, because I'm forgetful, is I'm going to go up here to File, Save As, and then I'm going to navigate to the desktop. And I apologize if I'm boring you. Go here, and actually I don't want to call it Video 1, I'm going to call it Video 2, so let me rename that. But the Video 2 will have everything in it from Video 1. And I'm going to call this first schematic Ohm's law. I'm going to go up here to resistor, drop down a resistor. I'm going to go to this AND gate, this component. I'm going to select that, and I'm going to grab a voltage source, plop it down. What if I hit Control E? What does that do? mirrors it, right, left and right, or rotates it, Control R. Okay, now I'm going to grab my little wire here, go around, come back around here, go up. Now let's put a value in here for voltage. I right-clicked on that, got 9. Let's do it a different way. Let's double-click, or right-click, put the 9 in that way, 9 volts, and let's put volts. Let's live it up. Doesn't matter. And then over here, let's put 1 kilo ohm, 1K. Okay, so before I go on, if I look at my little schematic here and I draw the values in, and this is 1K, how much current flows? 9 over 1K, 9 over 10 to the third, 9 milliamps. But we're going to verify that. Questions? Okay. So let's go. Now, notice there's a couple of issues here. All of the current, all of the electrons that leave the minus terminal and go over here to the plus terminal, they flow through the wires. It's a circuit, circuital, okay? There's no reference or any ground here, so let me plop that down, put a ground. Now let me put a wire to there, and let me ask you, okay, this is probably an advanced question. Probably some of your senior students don't know, but if I ask you how much current or water flows down this ground and why? Remember, if current flows, it has to have a place to flow, right? There's no place for this to flow, it's just a reference. It's like when I build a house, I've got, if you've ever looked and put the foundation in, you put a piece of rebar around in the foundation and you tie that piece of rebar, the metal bar, to the breaker box through a copper rod. All that's for is to provide a good foundation or foundation or ground. It doesn't allow current to flow there because there's no place for it to flow unless you're standing in a puddle on the floor of your concrete house, and then current can get back through you to a circuit and shock you. Okay, but just the house by itself, there's no way to control it to finish the path. So I put the ground in here, and actually let's try to run the sim without the ground and see that it doesn't work. Let's hit the run button here, and it says how long, what kind of simulation. What is transient simulation from last time? What's a time? It says what's the voltages look like over time. Okay, so I'm going to just put, I don't know what I'm doing. Let's just put 1 second. Okay, what's going to happen over 1 second? So I hit OK. Notice the syntax here, .tran1. I hit OK, and it says circuit does not have a conduction path to ground. Please flag a node as ground. Okay, well, let me get the big hand here, which is move it out of the way, and then come up here, dropping my ground out. Let's put it in a different place. Doesn't really matter where we put it. Connect it up, left click, oops. And I get out my scissors here. Boom. Hit the fit. Poke the running man again. It worked. Okay, but I don't know what the circuit's doing, so why don't I probe some things? Let me probe this node here. What do you expect it's going to be? 9 volts. This is a trivial question. If you see a voltage source to ground and somebody says, what's the potential up here? You don't think deep. It's 9. Okay? You don't let, even if there's a zillion wires going all over the place, it's 9. So let's verify that. 9 volts. What if I come over here and probe? What do you think? Oh, it won't even let me probe this node. Well, if I could, what would it probe to? 0. So let's pause. Pretty simple circuit. V1, 9 volts, connected to 1K. Let's go to View, go to the SPICE net list. It says I've got a resistor R1 from this node or this wire N001 to 0. And what does 0 represent here? Ground. Ground is always 0. Okay, so it's 0 and it has a value of 1K, and then I've got V1 from the node N001, 9 volts. First line is always ignored. If you ever get into integrated circuit design, you're designing chips, you have to be able to look at a netlist because it allows you to troubleshoot what's going on. I don't like this N001. I don't have any feeling for that. So what I'm going to do is go back up here, grab this little thing here, label net, and I'm going to call this, hey, I'm going to call it the same as I called the voltage source, V1. And I hit fit, and I look at the net list again, SPICE net list. Oh, now R1 goes from V1 to ground, and V1 goes from V1 to ground, and it's 9 volts. Questions? Easy, right? Okay. What was it if I wanted to save this simulation, or let's say I wanted to, let's run it first. I wanted it to automatically plot next time. What do? Click on what I want, go select the window, hit save. Then if I save the changes to the schematic, if I go into this V2 and I do Ohm's law, this PLT is the plot information. I open it up, I hit run, and there it is. The reason is as you're doing these complicated circuits throughout class, it's much easier if you can draw it once and then copy and then rerun it. And then if you, I want to see if I got the homework problem right, modify your stuff, reconnect it, rerun it. You know what the answer is before you even do the hand calculation. Okay? All right. So let's do a couple more things here. How do I measure the current through the 9-volt source? Let's put the cursor over here. Notice which way it defines as positive. That can be frustrating if you got a homework problem that says find the current and it puts it the other way through the 9-volt source, because when you do your simulation it's going to give you a negative. Another thing I can do is I can select this window and go up here and pick the trace. And I can see, I of V1, and I get minus 9 volts. And if you watch the first video, you know it's minus 9 because SPICE defines positive current flow as from plus to minus. But my homework problem said, what is the current? And it drew an arrow going the other direction. So what I'm going to do is I'm going to modify this. I'm going to get this little hand here, which is the stretchy hand. I'm going to zoom out a little bit. I'm going to grab it, pull it up. Then I'm going to get this little copy button here. I'm going to come down. I'm going to grab this. I'm going to pull it over here. Get the big hand again, the move hand. Grab it, and I'm going to do a Control R. I'm going to drag it over here. I'm going to change this to 0. So wait, before I go on, putting that 0-volt voltage source, how did it change anything in my circuit? What is a 0-volt voltage source? A wire. Okay, so it doesn't change anything, but I've put this source in here, and I'm going to rename it. All voltage sources start with V. I'm going to rename it measure. Now I can measure the current as being positive, as flowing from plus to minus. So now my homework, when I plot this V measure, that'll be the current flowing in this direction. So I rerun the sim. I come over here. It's in the right direction. Have I changed the circuit? No. Easy, right? Could also plot the current flowing in the resistor. Notice it goes this direction. Can everybody see that? If I grab that, what do you think would happen if I get the drag? If I drag it, it stays connected. But if I get the big hand, the move, and I drag it over here, and I hit Control R twice, put the resistor back in, and you remember this is like a pipe. It's like a constricting diameter pipe in a water analogy. There's no reason I should connect one side over the other. It's the same way, but when I rerun the sim and I look at the current, now the current's flowing in the opposite direction through the resistor. Questions? Does it seem reasonable? What was the other analysis that we did that you could use for measuring currents and such? If I didn't want this, I could go up to operating point maybe. If I do that and I hit run, then it just tells me what everything is. I can cut that out, put it in my homework, find out what the solution is. I can go back to DC. We're not going to do that. I'll do that in a moment. But before I move on, I'm trying to make it very simple so that you have a tool to help you when you're doing your more complicated problems. Yay? Okay. So now I'm going to save this, and I'm going to do File, Save As. And I'm going to call this one, how about we call it, let's make it a little bit more complicated. Let's call it Ohm's parallel law. I don't know, whatever. I don't like all this extra circuitry, so I'm going to get out the scissors. I'm going to cut this. I'm going to get the little hand, drag this back down, move this up, make it look pretty. Throw another resistor in here. Should we copy? Yeah, let's just let's copy. Oh, R2. Okay, so we go up like this, over, so forth. Now we're going to analyze this circuit. Okay, so what's the pressure or the voltage across this resistor? 9 volts. Gee, you're not challenging me. What's the pressure or voltage across this resistor? 9 volts. Oh, you're boring me. What's the current through here? 9 volts across 1K. 9 milliamps. What's the current through here? 9 milliamps. What's the total current supplied by the voltage source? Supplying 9 there and 9 there, so it's 18 milliamps. Oh, tough, right? All right, so before we do anything else, let me just point out something. When I was learning circuits that I found helpful, I never liked looking at these straight lines. I always liked to think about, if I were wiring it up, how would I wire the resistors in? If I was wiring my house, how would I wire the resistor, or the wiring through the wall? I don't have it going like this always. It could go up and over, around, if it had to go through a doorway or something like this. Would there be any difference in the circuit if I were to pull this guy over? Oops, let me zoom out a little bit. If I were to pull this guy over here like that, does the circuit change any? Does our analysis change any? No. So when you're looking at circuits, it's good if you think of, how do I arrange the circuit so that it makes more sense to me? Because you're going to do things like source transformations, where you're going to have to take one resistor, move it over. If I take this one and I slide it over here like this, and I take this and I come over here and I come over here, and I take this one, I go like that, and then I take this and I move it up, take this, move it down, and I get my minus here. And then I connect the wire back up. Isn't that the same exact circuit that I just drew a moment ago? Everything's exactly the same, still 9 milliamps through there. Let's verify that, actually. So let's go grab this. My mouse is having problems here. And let's, that was a little bit too much. Let's grab that, move it back. And then hit save for ohms parallel, hit run. Then let's see what the current flowing through here is. What do you expect I'm going to get when I plot? Be precise. Look at the way the arrows are pointing in the current meter thing. It's pointing down, right? So I'm going to get minus 18. So let's verify that. Okay, if I come up here and I plot, watch what happens. I'm going to plot and I'm going to get a voltage. Voltage over here is 9, and then it put the current on this side is 18 milliamps. If I can't see the voltage, I click on it. There it is. If I want to see the current through this resistor, I come down here and I can flip it around if I want to see positive. And I see that it's minus 9. Current through here is minus 9. Hit save. Okay, so I want to analyze this a little bit more and make it more generic. Does anybody have questions? Does it make sense? Or is it I'm in pain, shoot me? All right, so let's analyze this a little bit clearer because I want to make it more generic. What I'm going to do is I'm going to just draw a voltage source. We'll call it V1, and then R1 and R2 in parallel, and I want to give you what's called the current divider equation. So let's see. So there's our voltage source, V1. There's our resistor. Is a piece of wire a resistor? Yeah. It's just like if you look at your house and you're wiring your house, you got to get the right gauge of wire. If you use too narrow wire, then what ends up happening is you have too much resistive drop through the wire and you don't supply your 120 volts to the outlet. So let's call that R1 and R2. Let's put our ground there. And let me ask some simple questions, since I'm the king of trivial questions. What's the voltage right there? You know, that's something, if you're taking a test and somebody says, what's the voltage? And like I said, there's a voltage source to ground. You don't think deep, V1. If I ask, what's the current through here? Well, I1, but let's call it V1 over R1. What's the current through here? V1 over R2. If I look here and I say this is I total, and I ask you what is, and let's say this is I1, let's whip out the math here. If I ask you what is I total equal to in terms of I1 and I2, you know how I don't think deep here. I say water flowing pipe splits. This water equal this water plus this water. And that has a fancy name in circuits. That's called Kirchhoff's current law, KCL. And I did it at this node. Does it bother anybody if I draw a big circle around that node? How about if I do this? I'm trying to make those connect. Isn't that the same circuit? Couldn't I draw it around that node? Same exact thing? Okay. Let's make it a little bit more complicated. Before I do that, any questions? All right, so if I want, I could say that, actually, let's do it like this. Let's say that I have V1, and then I have, let's call this REQ for R equivalent. What's the potential right there? Yeah, I want you to say V1, you're boring me. I don't want you to be hesitant. I want you to be confident. V1. What's the current through here? There you go. And what I want to do is I want to find out if I want to place these two loads, what I'm supplying pressure to, with an equivalent load, how do I relate R1, R2, and REQ? So I could say this, if I want them to be equivalent, what would be the current flowing in the circuit here? IT. It's IT. So would everybody be okay if I wrote V1 over REQ equals IT equals right on? So tell me what to do next. I'm having flashbacks to 8th grade algebra, or wherever you took it. Cancel that. And then I come up here and I go, wait, I got an equivalent result. I can write 1 over REQ equals 1 over R1 plus 1 over R2. And these are how you combine resistors in parallel. In fact, we'll do a quick example, but if I have many resistors in parallel, for parallel resistors. Okay, so let's talk about filling up swimming pools before we go on and do an example. Let's say that I have a swimming pool, and let's draw it. I hate swimming pools, so I've had one all the time, and all they are is a big hole in the ground you throw money into. Especially you're out there cleaning them and throwing the chemicals in, and it's good to have friends with swimming pools. All right, let's say that I have a hose, and this hose can fill up the swimming pool in 10 hours. Say I have another hose that can fill up the swimming pool in 20 hours. How long will it take to fill up the swimming pool with both going at the same time? Yeah, 1 over 10 plus 1. It's the exact same problem as the parallel resistors. Has everybody got that? So if I say, what's the total? I time total, it's 1 over 10 plus 1 over 20. It's not 15. If that's what popped into your head, that gives me a heart attack. Because if I could take 2 of them and do one with 10 hours, it's not going to take 15 if they're both going at the same time. It's the same exact problem as parallel resistors. Any questions? So I don't want you to think there's anything funny with those parallel resistors. All right, so let's pause. Let's go back over here. Let's open up our, how come I didn't delete that? We don't want to zip that raw file up. And let's go to parallel, and let's say, you know what? I want to show you another trick here. Let's grab this copy. Actually, let's just copy one resistor. And I want to verify that statement I just made. So if I have 1 over 1K plus 1 over 1K, what's the total resistance? 500 ohms. So I'm going to change that to 500. Then I'm going to grab 2 wires. And I'll put one here and one here. And I want to teach you something here. Let's go grab the ground. Put the ground in. Let's grab this name here. Call it VN, or V1 rather. So let's right click and call it V1. Here's how you create frustration. These 2 nodes are now connected. It's exactly like I connected a wire from here to here. These 2 nodes are now connected. Let's prove it. If I go to the wire and I right click on the wire and I hit highlight net, if you don't understand this, you will get frustrated when you're doing your circuits, especially if you copy one and you copy it to another place and it has the same node names. Right click, highlight net. If I grab the stretchy hand, the pulley hand here, and I ask you now, trick question, see if you're paying attention, how much current flows down here to ground? None. Where does the current through this resistor flow? Flows like this, back over here, but you don't see the wire even though they're connected. So what's going to happen to the current in the voltage source now? It was 18. What's it going to become? 36. Anybody not follow that? Anybody follow it? All right, so let's verify that. Let's hit run. Let's go boom, 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 and then hit save, and we're good to go. Any questions? All right, we ready for a more challenging circuit? Now this one is called a voltage divider. For some reason, I don't know why the students never remember it, but you use it over and over again. And I'm going to do it several ways. But you're going to help me derive the equation. So here's my voltage source. Oh, you know what? Before we do that, let's do one more quick example. You know, if I have a voltage source like this, and this is 9 volts, the pressure here is 9 volts. Would it be reasonable if I did this instead? Is it reasonable to ground the positive terminal of the battery? I always think of ground as being connected to the negative. Does anybody here have a diesel? Diesels use a positive grounded battery, okay? What's the potential I have right here? -9. It's that easy. What's an example? If I take a drink of my soda and I blow into it, I'm putting in a positive potential. If I take a drink, I've got a negative suction and negative potential. It's the same thing. Don't let that being grounded confuse you. It shouldn't. If I ask now, what's the voltage across here? Well, plus minus 9 plus minus minus 9. Those are the exact same things. If I see a minus voltage, it just means I can change it to positive and flip the plus and the minus. Does everybody follow that? So if you if somebody, like when you're using chips, you might say, oh, this is connected to plus 9 volts. Well, that means you go to the source and you connect it to the battery like this. And then you might have minus 9 volts, and then you go connect it to the battery like this. Let me make sure I get it right. Minus plus, you ground the positive. How much current flows in this ground, this reference? All flows like this, right? This one flows like this. This one flows like this. How much current flows into here? Nothing. Does this confuse anybody? Should we do an example? You got it? All right, we'll see. Okay, so let's do another circuit. Something a little more challenging. Here's my battery. We like 9-volt batteries because we can imagine those. Now I have 2 resistors. Okay, so I did the parallel combination. If I were to ask you what's the equivalent of these 2 resistors, what would your answer be? R1 plus R2, right? Does that make sense? Okay, so now here's the thing. If I ask what's the current that flows in this circuit, what is it? Yeah, I'm not challenging you, I apologize. 9 over R1 plus R2. Okay, so if I ask you now, this will take a little thought. Let's call this V out. If I ask you what is V out, and I'm learning circuits, so I'm going to go ahead and, I don't want to handicap myself. I'm going to write up here on my quiz or test V equals IR so I don't have to think too deep. V out is the voltage drop across that resistor. So the R is what? R2. What is the current? Let's call this V in. V in. We'll call it 9 over R1 plus R2. Or I can rewrite it as V in times R2 over R1 plus R2. This is called the voltage divider. You're going to memorize that equation, because you're going to use it over and over again. Just like Ohm's law. Questions? Okay, so let's do a circuit example and sim it. So this says let's pick something different. Let's go with 1.5 volts. Let's go with 1K, 2K. And what's the units of resistance? Ohms. And let's ask, what is V out and what is Vx? Or let's answer what those are. And let's live it up while we're at it. What is I? What's Vx? Yep. Okay, what's I? What's 1.5 divided by 3k? Now I'm going to do it slow on this time just because I want to make sure everybody gets it. So 1.5 over 3 times 1 over 10 to the third. What's 1.5 over 3? Yep, 1/2 or 0.5. What's 1 over 10 to the third? What are the units of current? Amps, so it's milliamps. Let's write it as 500 microamps. Or let's write it as 0.0005 amps. If any of this confuses you, you need to get it right now because it'll minimize the pain later on. Everybody knows I'm going to post the notes, right? Where am I posting them? Boom. And the sim examples and this video. So you can say he was a slow talker, it bored me. You can play the video and put it on 2 times and see how fast it can go and see if you can get it. It might be funny. All right. I think when I was a student, I used to find if I sat back and paid attention and not took notes, I got a lot more out of the lecture than if I gotta keep track of all the lectures. So that's why I always post my notes. Okay, so let's go verify that. Let's go look at the circuit. Well, let's see, we need one more thing, don't we? What is the last thing? V out. Well, we know what the current is, so we know that the voltage here is going to be 2K times 0.5 milliamp. What is that? What's V out? 1 volt. But you know what? I don't want to use that. Does everybody see I got a milliamp flowing through 2K? I want to use my fancy-dancy equation right here. This voltage times the divider gives me that, so let me write it again. V out equals 1.5 times 2K over 1K plus 2K, which is 3 over 3 volts. So V out equals 1 volt. Yay or nay? What time are we supposed to stop? 3:30? Oh, get more than your extra 50 minutes, huh? Okay, any questions on this? Okay, so let's do it several ways. Let's go and let's call it, you know what, let me do it from scratch one more time. Get rid of this. Go to this. Open her up. File, save as, or new schematic. File, save as. This little screen drives me crazy. Desktop. There we go. Let's call this, how about voltage divider, something really unique. Let's see if I can do it fairly fast. Bang, bang. Go up here, component, voltage. Okay, drop it down. Right click here. 1.5. This one was 1K, 2K. Put the ground in. Yeah, let's put it in the middle here. Come over. I want to turn in nice looking homework, so I'm going to make this pretty. I'm going to make it match the solution or the problem that I had. I'm going to go draw a wire here, hit escape, draw a wire here, hit escape, go up here, call this VX, put wire right there, drop a VX there. Okay, so if I were to simulate this, what would be the current through R1 and Y? I don't want you to have pain. Pain is bad. Gratuitous pain. What's that? 0. Why would it be 0? If I highlight these two nodes, They're shorted together. There's a wire across that resistor. It's the same exact thing as if I do this. Water's flowing. Is it going to go through the water, or current's flowing? Is it going to go through the wire here, or is it going to go through this constricting area? It's all going to go through that wire. It's a short circuit. I'm shorting across it. That's bad. Does everybody get that? If you put a crowbar across the battery on your car, you create a short circuit. You get lots of sparks, right? You don't want to do that. Well, maybe you do because it's fun. I don't know. Okay. So I right click on this, and I'm going to rename this to V out. And let's see, what did I name? We didn't call this. Okay, so if I look at the circuit, which do you feel more comfortable? Do you want to see text or do you want to see plots? Text? So let's do both. But instead of hitting the running man and putting in the analysis, I'm going to do it like this and just put .op. Nah, let's do it this way. Let's hit the running man and select operating point, say OK. And then it says Vx is this node right here. It's 1.5 volts. V of V out, this node here is 1, just like we calculated. Current through R1 and R2 is 0.5 milliamps. Current through V1 is also 0.5, and the minus sign does not confuse me because I know SPICE defines positive current flow as plus to minus. Yay or nay? Is it making sense? Okay. So let's do it the other way now. Let's hit save. And let's right click on this. And then let's go to transient, select 1 second, something arbitrary. Nothing's changing here. Hit save. Hit run. And then let's plot, or let's do it this way. Let's plot V of Vx. What do I expect to see? 1.5. Let's press Control and plot V of V out. What do I expect to see? 1. I can hit, then I can go back over here, and then I can click, or I could plot these again, but I could use manually, click here, and I expect to see 1 point, or where's the current? I of R1, I have 0.5 milliamp. Okay, any questions? So let's say I want a precise value. I'm going to hit save. I'm going to right click here, and I want to know what's the precise value, and I'm going to go to attached cursor, and I'll say put the first one on there. Say OK. Then I can, let's drag it so you can see. I can say, what does it say? Oh, it's always exactly 0.5 milliamp, 500 microamps, 0.0005. Drag it around. I could go up here and say, oh, I'll put the second cursor on that green trace. And then come up here, drag that cursor around, and it's always at exactly 1.5 volts. Is it good? One more example, and then we'll do one other device and call it a day. Are you getting everything out of this? Does it seem challenging, or is it like, holy crap, that's so easy, why is he boring me? All right. Let's do one more challenging example. Well, it won't be challenging because you're all Ohm's law gurus now. So when you cover this in class, you'll be like, oh yeah, I know what he's doing. Okay, let's pick a circuit like this. Now I'm going to leave it a little bit algebraic because I want to explain some simple algebra tricks too when you're doing circuits. Let's call this Vn. Let's call this R1. R2, R3. Okay, so first question, see how lazy I am? I didn't draw a wire between here and here. But they're connected, aren't they? Yeah, so, but we're learning circuits, so we need to have actual circuital paths, so I'm going to go ahead and draw the wire in. Now, it says find all voltages and currents in the circuit. So let's start out with the easy one. Your class isn't until 4. You're welcome to come in and sit down. All right. I've got to do makeup lectures this afternoon for my other 2 classes because I'm going to be missing some time. All right, so what is, let's label some nodes here. Something easy. What should I label this node as? V in, right? So let's put V in there. What about this node? Let's call it VY. What about, okay, so are there any questions? Let me ask you this. If I make REQ equal to R1 in parallel with R2, or I make 1 over REQ equal to 1 over R1 plus 1 over R2, or I make REQ equal to R1 times R2 over R1 plus R2. Did I just repeat myself 3 different times? I mean, isn't that the exact same thing? If I solve this for REQ, I get this. I could rewrite it. I'm lazy. I'll often write it like this. Okay. Wouldn't I be able to draw a circuit that looked like this? What would I label this node here? VY. It's the same thing, right? What would I label this node? VN. It's the same exact circuit, right? Except I've got the current splitting here. So I could solve for VY. Once I have VY, how do I determine the current through each of these? Well, let me back up. Does everybody agree this VY and this VY are the same? If this REQ is the parallel combination of these 2 resistors? If this was 1K and this was 1K, what is REQ then? That's a trick. If you ever have resistors in parallel and they're the same value, you just have their value. So 77 ohms, 277 ohms in parallel are 33.5 ohm equivalent. So you just have the value. So if I say 1K and 1K, it's equivalent to 500 ohms. If I replace this 1K, 1K with a 500, don't I get the same voltage? Okay, is everybody okay with that? So if I go back and I ask you now, well, let's see how many ways we can analyze this. We could rewrite over here VY equals VN times R3 over R3 plus REQ. What did I just use? Voltage divider equation, which you're all going to memorize because you're going to see it 6,000 times, just like Ohm's law, and you don't want it to bog your thought process down. If I move this resistor and I move it up here so that it's flat and I have a wire coming down there, is it the same circuit? If I just slide it up and around? Yeah, I'm just thinking of it. It's the same thing, a voltage divider. Okay? If I come over here, so this is voltage divider. If I come over here and I ask you, what is the current through there? We only know 2 things in this class. Ohm's law, voltage dividers. Well, I guess we know 3 things. We know equivalent resistances too, combining them. What's the current through here? No, just in terms of VY and R3. I'm handicapped. I need V equals IR, or you know what? I'm even more handicapped. So what's the current through there? VY over R3. Any questions about that? What about the current through here? Oh, this one's tough. The pressure on this side is what? Vn. The pressure on this side is Vy. What's the difference in pressures across the resistor? Vn minus Vy. I've got some air tools in my garage. My compressor puts out 60 psi, but I put it through a real narrow pipe, and by the time it gets over to my hand tools, it's down to 50 psi. What's the pressure dropped across the pipe? 10. It's the same thing. Okay, no difference. So it's Vn minus Vy all over R1. What's the current through here? Vn minus Vy over R2. Does anybody not follow that, or does anybody follow that? Nobody follows it? Lay it on me. Yeah, this wire, you assume everything's the same pressure. Yeah, same voltage. These drop some pressure before it gets to this node. So there's a higher pressure here, then it drops as it goes down. Like you could say, oh, well, you screwed up. You didn't put wide enough diameter pipes to supply your tools. Well, you could run another pipe in parallel, and it would reduce the pressure drop because now you'd have two paths for the air to go through. So this is just representing an equal potential, or a point where the pressure is all constant. Okay. The same thing here. If there's no resistance and you just see a wire, you know in your mind the pressure, the voltage there is all the same. It's the same here as it is here, as it is here, as it is here. So I could redraw this and it all has the same pressure. If I go down here, if I have R1, then the current through there is this pressure minus that voltage minus this voltage, Vn minus Vy over R1. If I put another resistor in parallel, the current through here is Vn minus Vy over R2. And now I've got two paths for the air to flow, or two paths for the current to flow. The overall resistance drops, and it's R1 in parallel with R2. Yes? Yep, it's different resistances. What that means, since electricity likes to go the path of least resistance, you now know that simply means you'll get more current through the resistor that has the lower value. Yeah, yeah. It's like if I'm standing in a puddle and there's an appliance there, and the appliance, say it's a toaster, and the toaster heating element's on, and it's drawing a current, and I come up and I touch it and I provide another path, there'll still be current flowing through the toaster, but some will flow through me. It just splits and goes down. Okay, so that's why you have ground fault interrupters. Does anybody know? You've heard of ground fault interrupters? You know that on your power plug in like your kitchen or your bathroom, there's a set, test, and all that. That whole thing, that's the whole point of that thing's life, is to say, is any current flowing on ground? Because if there's current flowing on your ground, then you know there's another path and you want to pop the breaker. Okay? You don't want current on ground. That's why nowadays they have three wire connections, so that your water heater or your air conditioner or whatever, that's chassis is connected to ground. So you don't, in the olden days, it was very common. It happened here in Vegas all the time. Someone would have their water heater and it'd get corroded. They'd come up to repair it and they'd grab it and they'd die because it was corroded and the whole frame was floating at high voltage. So now they ground that, and then all the current goes in on the hot or out on the hot and returns on the neutral. Hot and neutral, nothing on ground. Okay? All right, we got 5 minutes. Let's do a numerical example on this. Let's find everything. But any questions before I go on? All right, we'll have to sim it. We'll do it fast. So let's say we got 1.5 volts. We've got a 1K, 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 and I want you to find all of the currents and voltages. So let's get partial credit. What's that voltage? 1.5. What is the equivalent resistance of these two in parallel? Anybody not follow that? And let's come down here, 1K. So if I draw my equivalent circuit, it's this. What am I going to use to determine that potential? Voltage divider equation, because it's burned into my head. Oops, I was lazy again. I'm so used to not drawing that connection because it clutters up the schematics. So I get Vy is equal to 1K over 1K plus 500 times 1.5 volts. And that means Vy equals 1 over 1.5. Somebody said it, I think. I can't hear too well with these on. 1 volt. Please, I'm posting the videos. I got the notes. If you're not following, this will make your life easier when you go through this in lecture. Okay, so what's the current through here then? If this Vy is 1 volt. What's the potential there? Yeah, V1 over R. So, but what's the potential here? 1. So I get 1 over 1K, which is 1 milliamp. The current through here and the current through here has to sum to 1 milliamp. So what's the current through there without doing any math, each one? Half a milliamp. So am I done? Yeah, let's say, what's the current flowing there then? 1 splits half, half, goes back to 1, comes back around, 1 milliamp. 1.5, 1 volt. Let's sim it and quit. Any questions? All right. 1.5, 1K, 1K, 1K. And let's go to, let's see, Ohm's law parallel, this one. Good enough. Oops, let's save this as file, save as example. Don't get too anxious, relax. All right, 1.5. Now I'm going to hit the little minus button here. Get out the scissors. Go down here. Drag this over. Copy this. Let's change it a little bit so it looks a little different. Get the wire out. Come up here. Go down, over. Hit fit. Is it the same circuit? All right. Let's hit save. Hit run. What do you want to do first? Nothing succeeds like success. So let's hit V1. Boom, 1.5. Let's hit Vy. Boom, 1. Let's look at the current through these. Oh, you know what? I don't like either of these the way they are. Let's flip them around so they go the same way. Control R. Don't worry, after a few classes with me, you guys will be like, holy crap, he's driving me crazy. Same old jokes and sayings. All right. So let's hit run. And then let's see, current through here. Let's see, what is it? Yep, right there, the red, 0.5 milliamp through this one. 0.5 milliamp through this one. 1 milliamp down here. Let's see, anything else we should look at? Let's hit save. Full. Any questions? Any answers? All right, we'll see you next week.